lecture, we have considered the representation of bounded linear functional on the Hilbert space H, as well as representation of sesquilinear form. And we have seen that a bounded linear functional, every bounded linear functional f on a Hilbert space H can be expressed in terms of the inner product x z, where z is uniquely determined by f and norm of z and norm of f is the same. Similarly, a sesquilinear functional, we have defined H from H1 and H2 are the two Hilbert spaces, and H is a mapping from the Hilbert space H1 cross H2 to K, a bounded sesquilinear form. Then H can be expressed as the inner product of S x y, where S is an operator from H1 to H2, a bounded linear operator, and is uniquely determined by H, uniquely determined by H and have the same norm as the norm of H. Is it not? This we have seen, these two. Now, these two representation will help you in introducing the concept of bounded Hilbert adjoint operator. Concept of Hilbert adjoint operators. With the help of these two results, we will introduce the concept of the Hilbert adjoint operator or Hilbert adjoint operator of a bounded linear operator T on the Hilbert space H. Okay. Now, this concept bounded Hilbert adjoint operator in fact comes when we study the matrices of and linear and differential equations. When we go through the linear differential equation or integral differential equation, all the matrices and converted in the form of the operators, then the concept of this Hilbert adjoint operator comes. In fact, we will see that in case of the finite, just like we say that symmetric matrix, Hermitian matrix and all these things, these will be the part of, means they can be related with these Hilbert adjoint operators. Okay. So, today we will discuss in detail what is the Hilbert adjoint operator of a bounded linear operator on a Hilbert space H. So, that is the concept. Okay. So, let us see the Hilbert adjoint operator. Let us see, first we define an Hilbert adjoint operator H. Let us suppose T be an operator. Let T from H1 to H2 be a bounded linear operator where H1 and H2 are Hilbert spaces, where H1 and H2 are Hilbert spaces. Okay. Are Hilbert spaces. Then the Hilbert adjoint operator T star adjoint operator T star of T is the operator from H2 to H1 from H2 to H1 such that for all x belongs to H1 and y belongs to H2, we have inner product of T x by equal to inner product of x t star y. Okay. It means, what is the Hilbert adjoint operator? It is basically the conjugate operator type. If T is an operator from H1 to H2, then an operator from H2 to H1 will be called a Hilbert adjoint operator, provided these two inner products are identical. Here T x by x is a map point in H1, T is an operator which maps the element of H1 to H2, by is in S. So, basically this is the inner product of H2. X is an element of H and T star is a mapping from H2 to H1. So, this is the inner product of H1. So, this is a well defined inner product both. Now, when these two values are identical, then we say an operator T star from H2 to H1 is a Hilbert adjoint operator T star. Okay? Clear? So, this is what now the question is, if T be a bounded linear operator, whether this Hilbert adjoint operator T star will exist, and if it exists, will it be unique, and existence and uniqueness is guaranteed, whether both will have the same norm or the norm will be different. Okay. So, in case if both are equal and having the norm same, then obviously it will be a useful thing. So, we have a result which gives the guarantee for the existence of this Hilbert adjoint operator. Okay. So, what is the Hilbert adjoint operator T star? The Hilbert adjoint operator T star of T as defined above. Let it be this as defined, let it be by A, as defined by A is okay, as defined above or as defined by A, exist is unique and is a bounded linear operator with norm of T star is the same as norm of T. Let it be, this is say 1, this one is 2. Okay. So, what this theorem says that if a T is giving to a bounded linear operator, then there is a guarantee that Hilbert adjoint operator will always exist, and not only exist, it will be unique in nature, and the norm of T star and T will be identical. Okay. So, let us see the proof. Is it clear? So, let us see the proof. Okay. Let us start this as, suppose, consider the inner product of by T x as h of by x. Okay. I am considering a function h defined on the Cartesian product of what? By is an element of H2, x is an element of H1. So, h is a function defined on H2 cross H1 to k, because this is scalar. Now, this function is defined as by comma T x. Okay. Now, let us define this functional h from H2 cross H1 to k by this method. We claim that H is a sesquilinear form. It means H must be linear with respect to the first coordinate and conjugate linear with respect to the second coordinate. H is linear with respect to first coordinate, obviously true. Why? Because H is defined in terms of the inner product. H is defined in terms of inner product. So, it is linear with respect to y, with respect to the first coordinate y. Conjugate linear with respect to second coordinate y, it is conjugate linear with respect to x, because if I take h by alpha 1 x 1 alpha 2 x 2, then this can be written as by t of alpha 1 x 1 plus alpha 2, because this alpha 2 x 2. We cannot say directly because of t is given, but since it is inner product is conjugate linear with respect to the second coordinate and t is given to be linear, t is given, that is why it will be conjugate linear with respect to x also. This can be seen as it is y, t is linear. So, we can write alpha t x 1 alpha 1 t x 1 alpha 2 t x 2 as t is linear. Is it okay? Now, this can be written as y alpha 1 t x 1 plus y alpha 2 t x 2, and this can be written alpha 1 conjugate, because it is inner product. So, alpha 1 can be taken outside. So, it becomes conjugate by comma t x 1 plus alpha 2 conjugate by comma t x 2, and this can be written as alpha 1 bar. What is this? H of x by x is defined as a by t x. So, this will come accordingly h of by h of y what? X 1, is it not? Similarly, alpha 2 bar h of by x 2. So, this shows that h is conjugate linear with respect to the second coordinate. Is it correct? So, h is a sesquilinear form. So, if I introduce this in this fashion, let it be say 3, then h becomes a sesquilinear form. Further, we claim that h is bounded. H is bounded. It means bounded means a sesquilinear form is said to be bounded if mod of, this is our okay, a sesquilinear form h is bounded if mod of h x by is less than or equal to c times norm x norm y, where c is some real number and the minimum value of c comes out to be norm h. Is it not? So, using this thing we can say to find out the boundedness, let us take the mod of h x by, okay, and then prove that this is less than or equal to constant times norm x into norm y. So, what is the mod of, because mod of h by x, is it correct? This is by definition mod of by inner product by t x, but by Schwarz inequality there is relation between inner product and norm, it is less than or equal to norm by into norm t x. T is bounded, t is bounded, it is given. So, norm of t x is less than or equal to norm of t into norm of x into norm of y. Okay. So, c is nothing but norm t. So, h is bounded. Agreed?
Sir, we have taken the equation 3 from our last proof, na?
Yes. because we have already proved that any function sesquilinear form will be given in form of the inner product, where inner product will be h x comma by and s is an operator like this. So, I have considered a functional h of by x in the form of inner product. So far we do not know the h is a sesquilinear form, but if it is linear with respect to first coordinate and conjugate linear with respect to second coordinate, then it becomes sesquilinear. The linearity followed because it is an inner product, and T x, the inner product is semi-linear or conjugate with respect to second coordinate, but it is semi-linear with respect to T x, but we are interested in semi-linear with respect to x. So, T, because of the linearity, it will give this breakup into two parts, and immediately one can write this. That is why it is a semi. Okay. So, basically it is coming from the form of that, using that form. Is it correct or not? So, we get that this is a bounded sesquilinear form. So, H is what we get is norm of H. If I take this is H of by x, mod of this is less than equal to norm of T, norm of x, norm of by. Is it okay or not? This one. Now, this will be equal to norm of H. This is equal to what? H of by x over norm of x into norm of by. So, primum is taken over what? X, which is not equal to 0, by is not equal to 0, but when you divide, it is less than equal to norm T. So, what we conclude is norm of H is less than equal to norm T. Is it okay? So, this implies the norm of H is less than or equal to norm of T, but norm of H is equal to supremum mod of H by x over norm of x, norm of y, x is not equal to y is not equal to 0. Now, if this is true for all y which is different from 0 and all x which is different from 0. So, we can write this by t, this is equal to what is the by x. According to this third, the h x by is nothing but the mod of inner product by T x. So, this is equal to inner product of by T x divided by norm x, norm by. Supremum is taken when x is not equal to 0, y is not equal to 0. Now, let us replace by a particular value as T x. So, this will be entire thing will be greater than equal to mod T x over norm of x into norm of T x, and supremum is when x is not equal to 0, particular value. So, this is nothing but the norm of T x square. So, this will give the norm of T x divided by norm x, supremum x is not equal to 0, and that is nothing but what? Norm of T. So, this implies norm of H is greater than equal to norm of T. Combining this 1 and 2. So, 1 and 2 gives norm of H equal to norm of T. Okay? That is what. So, what we conclude is that we have introduced an functional, hence this functional H, which is defined as inner product of by T x, is a bounded sesquilinear form. Not only sesquilinear, it is a bounded sesquilinear form. Okay. But by Rh representation theorem, if you remember, what is this bounded sesquilinear form? This is of the form h of x by Yes, this is, yeah, this was the bounded sesquilinear form in this way. It means every bounded sesquilinear form will be represented in the form of inner product, where S is an operator S1 and S2. Let us compare these two. What is the comparison here? Hx by NL by Tx. Okay. So, basically you are writing that this by equal to Tx is okay. This portion by we are writing in terms of some operator, is it not? So, if I write here S as an operator T star, then what happens to this? This will be equal to T star by comma x, because by x, is it not? By x is, so h of by x is a by sesquilinear. So, by Riesch representation theorem, this h of by x, h by x can be expressed as inner product of T star by comma x, where S is replaced by T star, is it not? Just like here, no, you just see here, you just see here x comma by, then when you take h of this, what is the change? Change is coming, it is nothing but an inner product, where x is replaced by s of x, that is all. Here we are taking this this one h of by x. I do not know the right hand side, I am not. If I compare the right hand side along with this, what should I write? X will remain as it is, by will remain as it is, plus an operator will come. Okay. So, that is why S will replace by T star. Okay. But this image, the domain of T star will be what? H2? Is it not? And range will be H1. So, you can say that where T star is a mapping from H2 to H1. Is it correct? Na? Is a unique. Okay. Now, just like this, S is replaced by this, S is uniquely determined, this is unique. So, this is also is uniquely determined by T, is it not? By T, and have the same norm as the norm of T, because norm of S equal to norm of T. So, it is clear, but norm of T is equal to norm of H, this is proved, clear. So, what we conclude is that this,
sir, we are basically coming in reverse way. First we say that norm of T star is equal to the norm of H. And as we have proved the norm of H is equal
yes,
to norm of T, then
yeah, that is correct. So, we are getting this because of this, clear, this is proved. Norm of T star equal to norm of H, and then we got it. Okay. So, this shows that norm of T star equal to norm of T, because norm of T star, norm of T is norm of H, and norm of H and this. Okay. So, we are getting this. Is it okay? That's right. So, this proves that combining this we get third. So, conjugate and then T star is an operator. So, that proves the result, is it not? Because what we require to prove is that was that Hilbert adjoint operator T star of T exists. So, existence of T star is guaranteed because S is and replaced by T star, and existence of X is already proved in the representation theorem. Then it is unique because S is unique, so T star will be unique, and it is a bounded linear because S is a bounded linear, but T star will also be bounded linear operator, and norm of T star and norm of T will be the same. So, this everything is true, and this result complete the proof. Okay. Is it clear? So, we are using the sesquilinear form what representation here to identify them. Clear? Now, there are certain properties of this adjoint operator, Hilbert adjoint operator. In order to prove first lemma, we will prove the lemma first and then go for the property. what is the lemma is, let x and y be inner product spaces and Q is mapping from x to y, a bounded linear operator. Then Q is 0 if and only if inner product of Qx comma y is 0 for all x belongs to x and y belongs to capital Y. And B part is that if Q is operator from x to x, earlier Q was x to y, if Q is x to x, where x is a complex, x is complex inner product space and inner product of Qxx is 0, means both the coordinates are same, Qx comma x, 0 for all x belonging to capital X, then Q must be 0. So, first is of course very simple, because if we look the proof for the first, then what is given, Q is 0. So, if Q is 0, then basically the inner product of Qx y becomes 0 into x comma y, but 0 is a scalar. So, we can take x by 0 is scalar quantity, it can 0 operator. So, okay, I didn't let us see, can you write this thing as 0 comma y, 0 operator means it will send to 0. Now, it will be written 0 into w comma y, now 0 into w, now you can take, now this is 0, okay. One of the coordinate is 0 means entire thing is 0, that is what. So, this is 0 for all x and y, so this is 2 for all x and y. Now, conversely, suppose this is 0 x y, conversely if Qx comma y is 0 for all x belonging to capital X, y belongs to capital Y, okay, then replace y by Qx. So, what we get from here is norm of Qx is 0, which for every x. So, this implies Q must be identically 0 operator. So, this one part is very easy. What is the second part says, if Q is an operator from x to x itself, okay, and x is given to a complex inner product space, then Qxx 0 will implies Q must be 0. That is, the inner product of Qxx is 0 only when Q has to be 0, if x be a complex. If x is not complex, then this condition may fail. If capital X is a real space, then Qxx 0 need not implies Q equal to 0. So, note, in case if x is real, then inner product of Qxx equal to 0 need not imply Q equal to 0. Why? For example, if I take Q is a rotation operator, it rotates x to y by 90 degree, rotates x to y by 90 degree. So, they are orthogonal. So, Qx is perpendicular to y. Therefore, inner product of qxx will be 0. So, inner product of qx by will be qxx. Qx in qx by will be 0. X is it not? So, inner x here x, is it correct or not? So, qxx 0. While q is not equal to 0, because rotation vector cannot be, rotation operator cannot be 0 operator. It rotates an angle through pi by 2. So, x is a vector and qx becomes orthogonal to x. So, qx comma x, this inner product becomes 0, while q is not 0. So, what it says is that if qxx is 0 and if x is a complex, x belongs to a complex plane, then q must be 0. But if x is not complex, then q need not be 0, may or may not be 0. Okay. So, let us see the proof for this. So, proof for the second part. Okay. So, what we do is, let us assume q be 0 for v. Let us start q v, this inner product is 0. Okay. For v equal to alpha x plus y, this an element belonging to capital X, because x belongs to capital X, y belongs to capital X, and x is a vector space. So, the linear combination belongs to this. Okay. Now, this will be q v. Okay. So, what we get is inner product q alpha x plus y comma alpha x plus y is 0. Okay. And this will be equal to inner product q alpha times of q x plus y comma alpha x plus y, because q is giving to be a linear operator, is it not? Q is a linear operator. Q by q times y, by q is a linear. Q by, yes, this is q by, exactly. So, this is q by. Okay. So, this will be equal to inner product of alpha q x comma alpha x plus y plus q by alpha x plus y. Okay. Now, this will be equal to alpha q x, and this alpha can be okay, q x alpha x plus y, I am writing okay, then q y comma alpha x plus q y comma y. Okay. Now, again this will be written as, this alpha can be taken outside. So, alpha conjugate q x comma x, and then plus alpha q x comma y, and plus alpha conjugate q y comma x plus q by y. Is it okay? But q x x is given to be 0. So, this part is 0 and this part is 0. So, what is left is now, so we get from here is, so we get alpha inner product of q x comma y plus alpha conjugate inner product of q by comma x is 0. Let it be third. Okay. Now, if I take, because alpha is a complex quantity, so take alpha to be 1. So, what we get is inner product q x comma y plus inner product q by comma x is 0, and when alpha is equal to I, what do you get? Inner product of q x comma y minus q by comma x is 0, because I gets cancelled, alpha val means minus I. So, therefore, if I add, then what we get is q x by is 0. Agreed? Where x belongs to capital X, y belongs to capital X. Now, this is the previous result A part, if you remember. What is the A part? A part says if qx by is 0 for all x belongs to x and y belongs to x, then q must be 0. So, if there is the same, x is replaced by that is all. So, from by previous by part A, this implies q must be 0. Okay? Clear? So, this proves the thing. And when q is not, when x is not complex, then you have got a contradiction which I have shown earlier. Okay? So, that is this clear?
Sir, in case of when you take the alpha
Huh.
O is equal to 1, that is first case.
Huh, huh.
Okay. So, when you are taking alpha is equal to I,
Then this will be the I and this will be minus I, but I cannot be 0, na? So, that is why. Okay? Okay. So, this proves. Now, based on this lemma, we can establish many properties of the Hilbert adjoint operator. So, let us see various properties of the Hilbert adjoint operator. Okay. So, let H1 and H2 be Hilbert spaces. Hilbert spaces, and S is an operator from H1 to H2, and T is an operator from H1 to H2, and both are bounded linear operators. And alpha any scalars. Okay. Then we have the following property. First, inner product of T star by comma x is the same as inner product by of T x. X belongs to H1, y belongs to H2. Okay. Do you remember this definition? This is different from the definition. Definition says inner product T x comma y is x T star y. Is it not? That was the definition of the adjoint operator, Hilbert adjoint. Here we are saying T star by x, then T can be taken here and this. Okay. Second is S plus T star is S star plus T star, both are bounded. Then third, alpha T star is the conjugate alpha T star. D T star star is T. Norm of T star T is the same as T T star, which is same as norm of T square. F T star T equal to 0 if and only if T is equal to 0, and G S T star is equal to T star S star, assuming that H2 equal to H1. Here assuming H2, because otherwise this product is not well defined. Okay. So, these are the properties following. So, proof of this, let us see the first property. T star by comma x. We want this thing. So, we can write this as x T star by conjugate. When we make the conjugate, the order reverses, is it not? Now, you apply the definition of Hilbert adjoint operator. As per the Hilbert adjoint operator, T x by equal to x T star by. So, this will give T x comma by definition. Okay. But conjugate again give you by T x. So, this proves that. Clear? Second part, x plus t star. So, consider x s plus t star by. Okay. Now, by definition of the conjugate, because if S is a Hilbert adjoint operator, T is a Hilbert adjoint operator, both are, then S plus T will also be a Hilbert adjoint. Why? Because what is required is Hilbert adjoint operator, it should be a bounded linear operator from S2 to A. If S is a bounded linear operator from one space to other, T is also the boundary from H1 to H2, then some of these two will also remain bounded linear operators, and then you find the mapping from S star to H2 to H1, we will get the same. So, this is by definition S plus T x y, which is the same as H x y plus T x y, because linear property with respect to the first coordinate, and then you write it again x S star by plus x T star by, and add them up. So, we get S star plus T star by. Okay. Now, this is equal to this. Can you say this product is equal to this?
Sir, take them, here will be the some comma, like
X comma. So, can you say from here S plus T star equal to S star plus T star? Yes, because by lemma first part, lemma is saying, what was the lemma? Yes, lemma is saying this, Qx by 0 implies Q is 0. So, this is true for all x and y, is it not? So, if you take this one, say take it here. So, x comma s plus t star minus s star t star by equal to 0, and this is true for all x and y. So, this has to be 0, this minus this has to be 0, and we get this. Okay. So, this clear now. So, this by lemma. Then third part, let us see the third, C. C is alpha t star. We wanted to show alpha conjugate t star. This is required to prove, is it not? So, what we do is we start with consider alpha t star comma x y comma x, is it not? Now, this will be written as y comma alpha t x, but alpha is in the second bracket. So, conjugate sign will come, and this will be equal to alpha bar t star y comma x. So, this will be equal to alpha bar t star y comma x, and then again this is true for all x and y. So, we get from here is alpha t star y is alpha bar t star. Similar way, okay. Similarly, fourth d star d can be computed in a similar way, then no problem. Is it correct? No? Now, fifth one, E. What is E is t star t equal to t t star equal to now. So, first we have to define accordingly, so that the t star t and t, what is the t? T is a mapping from H1 to H2, is it not? This was the H1 to H2. So, t star will be an operator from H2 to H1. So, when we write t star t, it means first it will take the elements from H1, then it will go on T H1 will be the element of H2. So, basically it is from what? H1 to H1, is it not? H1 to H2, and what is T star? H2 to H2, okay. So, it means the domain of this and domain of this are not the same, but what it says is that their norm will remain the same, okay. So, let us see the norm of T, both are equal to the norm of T square, okay. So, consider norm of T x square. Okay. Now, this can be written as inner product of T x. Is it correct? And this will be equal to, start with this, so T star T x comma x, is it not? T star T x comma x. Now, T and T star both are bounded, these are given to be bounded operators. So, they are bounded operators. T star will also be bounded linear operator. So, this is a bounded linear operator. Okay. So, by the Schwarz inequality, modulus of this inner product is less than or equal to norm of this into norm of this.
T is bounded, T star is bounded.
Huh?
But what is the proof that the multiplication of these two will be again a bounded?
Bounded operator. That is, norm of T1 into T2 is less than or equal to norm T1 into norm T2. So, that will give the boundedness. Okay. So, that will be given. Schwarz. So, by applying the Schwarz, we get from here is now this is less than or equal to norm of T star T into norm of x into norm of x square, is it not? By this is norm of this into norm of this, again this is less than or equal to norm of this, because basically this will be like this, norm of T star T into norm of x, further it will be less than or equal to this, and we get this part. Okay. Norm of T star T, divide by norm x square. So, what we get it? This is equal to, so divide by norm x square and take the supremum. So, we get norm of T is less than or equal to, is it not? Clear? Is it correct or not? Now, this will be further less than or equal to norm of T star into norm of T. Is it right? Norm of T square, this is norm of T square, sorry, norm of T square. Okay. So, this will be equal to norm of T star T, which is less than or equal to norm T. But what is the norm of T?
Norm of T star.
T star is nothing but the norm of T. It means these two are identical. When they are two equal, so this implies norm of T star T must be equal to norm of T star norm of T. No? And basically both will be equal to norm of T square. Clear? So, this proves that result. Is it okay or not? Similarly, you can start with TT star. Similarly, start with norm TT star. In a similar way, you can show. Is it not?
In general, when we take the some norm, means norm of Tx divided by norm of x. The supremum of that. So here we have the norm of Tx square.
Divided by norm x square. So, basically it is norm of T square. Okay. But take the norm Tx by Tx and whole square, then take the supremum inside. So, you get it. Okay. Nothing. Clear? So, this proof. Now, what else is left now? Sixth. Okay. Then Tt star equal to 0, this f follows from here, from E. Why? Tt star is 0. Tt star is 0, automatically T will be 0 and vice versa. So, nothing is there. And G St star, this we have to show. Okay. So, consider x St star by. Okay. Now, this will be equal to Stx comma by. Okay. Now, this is equal to what? Tx S star by, and which is equal to x T star S star by, and this implies St star equal to T star S. So, order reverses, and so this completes your this part. Agreed? So, this. Okay. Now, there are, as I told you earlier, that this Hilbert adjoint operator, we can connect it this with our matrices, okay, operator. And in fact, in a particular case, our self adjoint operator, symmetric operator, they can be converted or can be considered in terms of this relation between these two. This self adjoint operator in a particular cases can be classified in three. Okay. What we have now, self adjoint, unitary and normal operator. The definition will depend on this. Classes of boundary linear operators, importance in this. So, we define as a bounded linear operator T, a bounded linear operator T from H to H on a Hilbert space H is said to be self adjoint or Hermitian if T star equal to T. Okay. Then unitary if T is bijective, means 1 1 on 2, bijective, and T star equal to T inverse. So, when T is a 1 1 on 2, inverse exists, and normal if T star equal to T star T. Okay. So, a bounded linear operator T on a Hilbert space is said to be self adjoint if the Hilbert adjoint operator of T coincide with the operator T itself. When T is a 1 1 on 2 and the Hilbert adjoint operator is coincide with the T inverse of the operator T, then we say it is a unitary, and when T star T star T is a normal. Okay. So, the Hilbert adjoint T is defined. Now, this is remark. Okay. If T is self adjoint or unitary, then T is normal. Every self adjoint operator is a normal operator, every unitary operator is a normal operator. Why? What is the definition of the normal? T star we wanted to T star T. So, if I write here T star, if it is self adjoint, then T star become T. So, what is the T star? T square, and what is this? T square, same. So, self adjoint operator will be normal operator. If it is unitary, then T star is nothing but T inverse. So, T star becomes I and T star T also becomes I. So, basically every self adjoint unitary operator is, it means self adjoint implies the normal, unitary implies the normal. Okay, but normal operator need not be self adjoint or need not be the unitary. Clear? Converse need not be true. An operator may be normal, but it need not be a self adjoint operator or unitary. For example, if we consider an operator I from H to H, an identity operator, and T I consider to be 2 okay, consider t. Then what we claim is t is normal. Why normal? Because what is the t star? T star is 2 I star, and this will be equal to what? Conjugate of this minus 2 clear. So Tt star becomes what? 2 I 4 I square, that is 4 into I, and that is the t star t also. So t is normal, but t is not self adjoint. Why? Why self adjoint? Because t star is equal to t, because t star which is coming to be minus 2 I is different from 2 I, that is t. So it is not self adjoint, it is not unitary. Why? Because what is the t inverse? T inverse will be minus I by 2I, because t into t inverse should be I. So this gets cancelled to n I square. So t star which is not equal to t inverse. So it is not unitary. Okay. So this, thank you.